Hello everyone, my name is Yi Zhang and I'm a PhD student from Arizona State University. Today I will be presenting our work on reinforcement learning for beam pattern design in millimeter wave and massive MIMO systems. This is joint work with my colleague Mohammed Arabia and our supervisor Ahmed Aktib. So first, let's start with motivations. Beamforming is a very important technology in enabling millimeter wave and massive MIMO communications. First, because of the severe path loss in high frequencies, adopting large number of antennas at both transmitter and receiver, and together with beamforming, are crucial in providing high receive power. Second, interferences like multi-user interference and intercell interference put a limit on the performance of massive MIMO systems. However, as shown in this figure, if we can perform beamforming accurately, it can significantly decrease the interferences by focusing signals to the target users without interfering others. However, to achieve its full potential, accurate channel state information is normally needed, but this is difficult for the following reasons. First, due to the hardware cost and the power consumption, analog-only or hybrid architectures are normally adopted, which makes the channel estimation process different than the sub-6 systems, where each antenna has its own RF chain. Second, downlink channel state information is normally hard or expensive in terms of training overhead to acquire in FDD massive MIMO systems. And third, current channel estimation process normally assumes ideal hardware or the hardware is well calibrated. However, the hardware calibration is an expensive process, which means that assuming ideal hardware is not practical. The prior work on both analog-only beamforming and hybrid analog-digital beamforming focus either on assuming known and ideal array geometries, or they would just select the analog beamform vector out of a codebook that is comprised of narrow beam steering beams. However, in reality, the hardware or the array geometries might not be ideal and might not be known, and also having just narrow beam might not be optimal. For example, if we have a propagation scenario with multiple dominant passes, maybe the optimal beam will have multiple lobes. So this motivates the need to develop beam pattern learning solutions that are capable of learning complex beam patterns that adapt to environment and for arrays with unknown or arbitrary geometries. So in our paper, we consider a fully analog system where we assume that the base station has M antennas and adopts quantized phase shifters, meaning that the phase can only take value from a discrete set. For example, with a 3-bit discrete phase shifter, the phase values can only take from this set with 8 different values. We also adopt a general geometric channel model, and we assume that the channel between mobile user to base station is a summation of L passes with different path gains and angle of arrivals. Besides, we also take into account the hardware impairment, where we assume there is unknown and uneven antenna spacing, and there is unknown phase mismatch incurred at each antenna. So for an ideal ULA, the array response vector takes this form, and for a linear array with unknown and uneven antenna spacing and phase mismatch, as shown above, the array response vector takes a different form. So in our channel model, the array response vector admits different definitions in different scenarios. It's worth mentioning that although we evaluate the proposed solution with respect to these two main characteristics of interest, our solution itself is general. So if the base station wants to transmit the symbol X to the mobile user, it first goes through all the phase shifters to get shifted, where we define the analog beamform vector to this form. We normalize it to make it valid for performance evaluation, and then this symbol gets transmitted by using this beamform vector to mobile user. The signal received by the user can be written like this, and the received Asilomar as user can be calculated by using this formula. And we assume that the mobile user feed this beamforming gain back to the base station to indicate how good the current transmission is. So our problem can be simply formulated as this form, where we want to find the beamforming vector that maximizes the average beamforming gain over a set of users, where H denotes the channel set that contains multiple similar channels, and theta is the discrete phase set. The first constraint is to support the fully analog system, and the second one is to uphold the discrete phase shifter hardware constraint. It's worth mentioning that the problem is hard to solve by using the classical optimization approaches for the following reasons. First, it is essentially a discrete and non-convex optimization problem. And second, when we view it from a discrete perspective, it features an extremely large feasible set. So for example, for a base station with 32 antennas and 3-bit phase shifter, there are over 10 to the power of 28 possible beamforming vectors. Moreover, the size of this feasible set will be increasing exponentially with respect to the number of antennas and also the resolution of phase shifter. And finally, there are unknown parameters, which are channels in the objective function, and the system has only access to beamforming gain feedback but not channels. When we see the problem in detail, it is actually pretty similar to that of reinforcement learning. First, the beam pattern learning problem is essentially a search problem in a huge discrete space. Second, the channel state information is unknown and the system can only resort to user beamforming gain feedbacks to know how good its current performance is. And third, the system needs to learn how to adjust its beam pattern based on user beamforming gain feedbacks. And reinforcement learning is well known for its powerful capabilities of searching and exploring. So with this motivation, we want to leverage the powerful learning capabilities of reinforcement learning to finally efficiently learn beam patterns that adapt to both environment and hardware. So in order to solve the problem in a reinforcement learning fashion, we need to first specify all those building blocks of the learning algorithm. So we define state as the phase of the beamforming vector and action as the change of the phase of the beamforming vector, where the phase can only be selected from the discrete set theta. And for simplicity, we directly assign action as the next state because they are all just phases. Also, we adopt a ternary reward mechanism where the reward at time t takes values from +1, 0, or -1, which is determined by using the following rules. The advantages of using such formulation can be summarized as follows. First, it respects the fully analog hardware constraint because we directly learn the phases of the beamforming vector but not the beamforming vector itself. Second, it respects the discrete phase shifter hardware constraint because we put a constraint on the action where it cannot take any possible continuous values but can only be selected from the discrete set theta. And finally, this formulation doesn't require any channel state information because from the definition of the reward, we have a threshold beta t, which starts from 0, and whenever the base station finds a beamforming vector that achieves the best beamforming gain so far, this threshold will get updated with this new gain. So it doesn't require any channel state information or even any statistics of the channel state. However, from the definition, it can be found that the problem actually features a very large action space, which makes the commonly used reinforcement learning algorithms such as deep Q-learning or deep deterministic policy gradient hard to apply. Therefore, we adopt novel architecture called the Whopper-Tinger architecture, and it is based on the actor-critic framework. And to make it suitable for exploring in discrete action space, there is a k-nearest neighbor quantization sitting between actor and critic networks. And whatever action predicted by the actor will first go through this kn quantization to make it valid, and then it will be passed to the critic network to evaluate the Q value. So in a similar fashion, we also adopt this actor-critic framework, and we input state, which is the phases of the beamforming vector, as mentioned before, to the actor network to get a prediction. And this prediction will first go through a quantizer because we only have discrete phase shifters. So the quantizer here is to make sure that all the predicted phases are implementable by the phase shifters. And then both the previous phase vector and the new phase vector will be inputted to the critic network to get a Q value, basically to indicate how good this transition is from the previous one to the new one. Also, this new phase vector will be implemented by the base station, and then the base station will transmit a signal based on this new beamforming vector to the users, and then we average all the beamforming gain received from users to get the reward, and this reward will be used to calculate the target of the critical network. Then we calculate the mean square error between the predict Q value and the target to update the critical network. Also, the predict Q value will be used to construct the policy laws to update the actor network. So this is a complete training loop of the learning model, and we can abstractly partition those components into a DRL agent domain and an environment domain. We evaluate our proposed learning algorithm in DeepMIMO, which is a publicly available dataset for deep learning applications in millimeter wave and massive MIMO communications, and we adopt the following basic parameters in our simulations. We use a scenario called O1_60, which is an order scenario, and is focused on line of sight connections between users and base stations, as shown in the figure. And the system is operating at 60 GHz, and we select the third base station, as shown in the figure. We assume that the bandwidth of system is 1 GHz and it is a single carrier system. Also, we construct the channel by only considering the dominant file passes. We consider two array architectures. The first one is an ideal ULA with 32 antennas, which is along y-axis and shown in the figure, and with half wavelength antenna spacing. And the second architecture is a linear array with unknown array geometry and hardware impairments. It has the same number of antennas, but the positions of the antennas are drawn from a Gaussian distribution with 0.1 wavelength standard deviation, and the phase mismatches are drawn from another Gaussian distribution with 0 mean and 0.32 pi standard deviations. It's worth mentioning that they are all unknown to the base station. Finally, let's look at the simulation results. We first evaluate the beam pattern learning solution on a system with ideal ULA as shown in the last figure. The learned beam can approximate the equal combining beamformer very well, or from another perspective, the proposed learning algorithm is capable of finding the location of the user in the line of sight scenario and forming a pointed beam to serve this user. In the right figure, we plot the average beamforming gain over the number of iterations. As can be seen, with less than 10,000 iterations, the proposed solution can find a beam that achieves around 80% of the equal combining upper bound, and with less than 50,000 iterations, it achieves more than 90% of the upper bound. It's worth mentioning that the equal combining beamformer achieves the upper bound in terms of beamforming gain in fully analog system, but it is based on two major assumptions. First, it assumes that the channel state information is completely known, or more specifically, the phase of each channel element is known. Also, it assumes that the system adopts continuous phase shifters. We next evaluate our proposed solution on a system with hardware impairments. This is a more practical scenario, and it's also the case that our proposed solution is mainly used for. As can be seen from the left figure, the learned beam can capture very well for almost all the main lobes of the equal combining beamformer, which is verified for its performance, as can be seen from the right figure, where the performance of the learned beam outperforms a 32-beam classical beam steering codebook with negligible iterations and achieves more than 90% of the upper bound with around 10,000 iterations. Actually, it is common that the performance of classical beam steering vectors degrades drastically when either the array geometry is not uniform or there is certain level of hardware impairments. Also, as mentioned before, our proposed solution is capable of learning beam patterns that add up to different array geometries and different hardware impairments, relying only on the beamforming gain feedbacks from the users. So to conclude this work, first, beamforming is crucial for millimeter wave and the massive MIMO systems, which is the motivation of this paper. And second, we came up with a learning frameworks that can design beam patterns that adapt to unknown array geometries and hardware impairments, and at the same time, it respects the key hardware constraint. More importantly, the designing process relies only on user beamforming feedbacks and avoids estimating the channel. And finally, from the simulation results, we can see that the learned beam achieves great performance. It outperforms classical beam steering beams in both cases, and also it achieves performance that is nearly as good as equaling combining upper bound. So in the future, this work can be extended to learning environment and hardware-aware beam codebook instead of just a single beam pattern. And also it can be extended to multi-user scenarios. Thank you for listening to this presentation. If you have any questions, feel free to reach us.